Welcome to Advanced Learning Tutoring. This is the chemistry playlist. Please like this video and subscribe to our channel. Calculating rates of reaction. The mean rate of a chemical reaction can be calculated by measuring the quantity of reactant used up divided by the time taken, or measuring the quantity of the product formed divided by the time taken. The quantity of reactant or product can be measured by the mass in grams or by a given volume in centimetres cubed. The units of rate of reaction may be given as gram per second or centimetres cubed per second. For those students sitting the higher tier paper, you may be asked to calculate the mean rate of reaction from a graph. Typically, graphs involving the change in the time versus the change in the quantity will give us a curved graph. Therefore, calculating the rate at a specific time, you must draw a tangent to that curve. A tangent is a straight line that touches the curve where approximately the areas either side of the curve are equal. Find the gradient of the tangent by doing the change in the y divided by the change in the x. You can do this using the triangle method, where you draw a triangle below your tangent to find the change in the y and the change in the x values. Investigating and measuring the rate of a reaction required practical. Depending on the reactants used, whether they are solids and liquids or two solutions, there may be a number of methods that you could use. In the case of magnesium and hydrochloric acid to produce hydrogen gas, you may be able to measure the mass lost of magnesium because the magnesium dissolves in the acid to produce hydrogen gas, or you could measure the volume of gas produced using a gas syringe or a measuring cylinder. Independent variables may be the concentration of acid. The dependent variable, the variable you are measuring, could either be the volume of gas produced or the mass lost in grams. Control variables would be the volume of acid used, the size and the mass of metal, and temperature and pressure. Using a graph, you can identify which is the fastest reaction from the line with the steepest curve or the line that produces the maximum volume of gas in the shortest time. If using two solutions, for example hydrochloric acid and sodium thiosulfate, reacting these two solutions together produces a sulfur precipitate. A precipitate is a solid formed from two solutions. Forming a precipitate will make the mixture go cloudy. Placing a cross drawn on a sheet of paper underneath a conical flask, you are able to time how long it takes for the cross to disappear. This involves human error, as if you repeated this experiment, you would need to ensure you press the stop button on the timer at the same shade of precipitate each time. Independent variables may be the concentration of acid used. Dependent variable, the time taken for the cloudy precipitate to appear. Control variables would be the volumes of each solution and temperature. Collision theory and activation energy. For particles to react, they must collide with a minimum amount of energy. This is known as the activation energy. Particles can collide unsuccessfully, meaning they have collided but not with enough energy for the reaction to begin. Therefore, particles must collide successfully with at least the activation energy for the reaction to begin. A number of factors can affect the rate in which a chemical reaction takes place. Concentration, surface area, temperature, and the addition of a catalyst. Increasing concentration or pressure in the case of gases increases the number of particles in the given volume. This will increase the frequency of successful collisions, therefore a faster rate of reaction. Increasing surface area of a solid, meaning breaking the solid into smaller pieces, increases the surface area to volume ratio, and hence increasing the area the particles have to react. A higher frequency of successful collisions and therefore a faster rate of reaction. Increasing temperature, providing a larger amount of thermal energy, particles move faster as they have more kinetic energy. Therefore, a higher frequency of successful collisions and a faster rate of reaction. A catalyst is a substance that speeds up a chemical reaction without being used up. It's not part of the overall reaction. A catalyst works by lowering the activation energy by providing an alternative pathway. Examples of catalysts are enzymes. Enzymes are biological catalysts that speed up the rate of digestion. Reversible reactions and dynamic equilibrium. In some chemical reactions, the products can react to produce the original reactants. These are called reversible reactions and are displayed with a double-headed arrow in the overall balanced equation. If the forward reaction is exothermic, the backward and opposite reaction will be endothermic, and vice versa. The direction of a reaction can be changed by changing the conditions. For example, increasing or decreasing the temperature may favour either the forward or backward reaction. When a reversible reaction occurs in an apparatus that prevents the escape of reactants and products, a closed system, equilibrium can be reached when the forward and backward reactions occur at exactly the same rate. When this happens, it appears as though nothing is happening in your closed system. The concentrations of reactants and products remain constant. A good example of this is on an escalator. If an escalator is travelling downwards and somebody is walking up the escalator at the same rate, it appears as though that person is not moving, but we know both escalator and the person are moving just at the same rate. They would be at dynamic equilibrium. Changing the position of equilibrium. This means that you can favour either the forward or backward reaction. This will depend on the number of molecules of the reactants or products, and if the forward or backward reaction is exothermic or endothermic. Le Chatelier was a famous chemist who says that the relative amounts of all reactants and products at equilibrium depend on the conditions of the reaction. If a system is at equilibrium and a change is made to any of the conditions, i.e. temperature, pressure or concentration, then the system responds to counteract the change. This means if the forward reaction is exothermic, for example, releasing energy to the surroundings, if you increase the temperature, maybe to increase the rate of reaction, the system will try and counteract the change by absorbing some of this energy. Therefore, the endothermic reaction is favoured. The effect of changing concentration. If the concentration of one of the reactants or products is changed, the system is no longer at equilibrium and the concentrations of all substances will change until equilibrium is reached again. If the concentration of reactant is increased, more products will be formed until equilibrium is reached again, and vice versa with increasing concentration of the products. The effect of changing temperature. If the temperature of a system at equilibrium is increased, the reaction will favour the endothermic reaction. If the temperature of the system is decreased, the equilibrium will shift to favour the exothermic reaction. As referring back to Le Chatelier, the system is trying to counteract the change. The effect of changing pressure. In gases, reactions at equilibrium, an increase in pressure cause the equilibrium position to shift towards the side with the smaller number of molecules. This counteracts the change that has been made. If you are increasing the pressure, the reaction will try and favour the side of the reaction which is at the lowest pressure, therefore the side with the fewest number of molecules, as pressure is defined as the number of molecules colliding with the walls of a container. A decrease in pressure causes equilibrium to shift towards the side with the largest number of molecules, again counteracting the change. Changing the position of equilibrium. An example question. In industry, ethanol is produced by the reaction of ethene and steam at 300 degrees Celsius and 60 atmospheres pressure using a catalyst. The reaction is reversible. The equation for the reaction is C2H4 ethene plus water H2O, the double-headed arrow to show that the reaction is reversible, producing C2H5OH, which is the formula for ethanol. The forward reaction is exothermic. Predict the effect of increasing the temperature on the amount of ethanol produced at equilibrium, and give a reason for your prediction. An increase in temperature will favour the endothermic reaction. As we have been told the forward reaction is exothermic, that must mean the backward reaction is endothermic. Therefore, more of the backward reaction will occur. Ethanol will be breaking down to produce the reactants. Therefore, the yield or amount of ethanol decreases. Explain how increasing the pressure of the reactants will affect the amount of ethanol produced at equilibrium. Looking at the balanced equation, we see there are 2 moles of gases on the reactant side and 1 mole of gas produced on the product side. Increasing the pressure will favour the side of the reaction with the fewest number of molecules. As an increase in pressure, the system will try and decrease the pressure by favouring the side that is at the lowest pressure, the side with the fewest molecules. Therefore, the side with the fewest molecules is the product side, the forward reaction. Therefore, more ethanol will be produced. The yield of ethanol increases.